I'm stood in front of the TecQuipment AF302. This is the continuous supersonic wind tunnel. This is one of two wind tunnels that we produce in the supersonic range. The first one, the AF300, is the intermittent wind tunnel, whereby we get between 5 to 6 seconds of runtime. However, as the title says, this is the continuous version where, providing it's switched on, you get a continuous flow of air. So looking at the major components, this is the inlet section here, shaped in such a way that we get a nice laminar flow of air, a nice clean flow of air. That is then drawn into this working section here. So this is where all the action happens. These liners fit in the top, and they ultimately determine the wind speed that we achieve in the working section. So there are a choice of three. The supersonic liner is already fitted in the top area there. We then have a slightly less profiled one, which is the Mach 1.8 liner. Then the shallow one, I call that shallow. This is the subsonic liner. So you have a choice of which wind speed, top end wind speed, you want to work with. Okay. When I use the word Mach number, this is a dimensionless number. It is just a number. And this number is determined by the speed of the object travelling through air, so that be it a plane, missile, rocket, whatever, divided by the speed of sound. We know the speed of sound is 767 miles per hour. So let's say the wind speed is travelling at 1381 miles per hour. If you divide 1381 by 767, that gives you 1.8. This magic number, Mach 1.8, and that is determined by that liner there, okay? So even with this giant vacuum pump and motor, that still isn't enough to get to Mach 1.8. So we introduce what's known as a nozzle. In this case, it's a Laval nozzle, where we have a sudden contraction and then a gradual expansion. This is enough to ramp up or accelerate that wind speed to the desired value. So moving along, that's the inlet section we just covered, and then the air is being sucked in, so it's a suction type wind tunnel, and eventually inside this enclosure there is a giant pump and motor that is drawing that air through the working section. If you want to have a look inside, you can just carefully have a peek inside where you'll see that giant motor and pump. I'll just do my shoelace up. So it's a pretty sizable pump and motor that we have in there. The enclosure itself, when it is shipped, this will go flat packed, obviously to save shipping costs and volume. Okay. So coming back to the experiment itself, experiment 1 is looking at the pressure distribution along this nozzle, and we achieve that because at the bottom liner, if you're able to zoom in on there, you can see some very small tappings. These tappings are connected to some tubes, and they lead back to a pressure display unit on the instrument frame, and we will be looking and observing these raw pressures, and with those pressures we can actually calculate the Mach number at each of the tapping, because we know the height of the working section, which is 100 millimeters. We know the width is 25 millimeters or 4 by 1 inches, and then we can calculate the area height ratio, and then after that we can calculate the pressure ratio at each of the tapping. So we have the raw tapping pressure, then we have a tunnel reference pressure, and that gives us a differential. And that reference pressure can be shown on that gauge there. So everything can be put back into VDAS. VDAS is not essential because you can do the calculation manually. However, it's desirable because it takes out any of the errors that can occur by pen and paper, and it gives you the ability to export your data to Excel. So it's a very powerful tool. Okay. And then the second objective is to basically look at the pressure waves or the shock waves around a model. And one such model has been fitted into this working section. So that's a single edge, 5-degree model. But with the equipment, you also get provided some other models, which I'll just go and grab. And these models are shown here. So we have a tapping model with 2 tappings to look at the pressure distribution on that model. Then we have 10-degree, 7-degree, single edge and double edge models, and those fit in the working section so you can observe the pressure waves or shock waves. And then finally we will walk around to the instrument frame. So this is where we would be operating the wind tunnel on and off, and also with emergency stop. The local pressures from the 25 tappings, and then a mimic of the nozzle, okay? And that's not the direction of the air, that indicates the 2 tapping pressures or points on the tapped aerofoil, okay? The actual air is travelling from left to right. So sudden contraction, gradual expansion, increase in velocity, reduction in pressure. So that's a useful diagram. And then you have the VDAS screen here. If you just have a quick look at VDAS, this is where we can capture the angle of attack, the individual Mach numbers, the raw pressures. We can export that data into Excel, which I did earlier. And if we just open that Excel spreadsheet, we can look then at the pressure tappings along that nozzle. So on the y-axis we have the Mach number, and on the x-axis we have tapping number, 1 to 25. You notice there's a bit of a peak. That's where we actually got over Mach 1.8. And I'm unable to describe or explain how that happened, but it did. So it's not a complaint in any way, because it just shows the power of this wind tunnel. And then finally, I did actually capture some video. It looks like I closed it off. Sorry, I closed it off. But there is an image here of the shock wave that I caught earlier. And you can see the formation of that shock wave. And from there, you will be able to print these images, take a protractor to those shock waves and do all the mathematical analysis and manipulation that comes with it. And that's the AF302.